Hello guys, welcome to this channel. So today we're going to talk about what is a half integer value. What's a half integer value in what we call a half integer spin, and this is in continuation with fermions that we are exploring. And if I take you back a bit so that you know what or where we are, let's define a fermion. What are half integer spin fermions? You know what a fermion is? You go back to the video and you'll watch the videos that we've done. Like what is a fermion in simple terms? What is a fermion? If I have to refresh your memory, a fermion is any particle that has an odd half integer spin, like a half, 2/3, and so forth spin. Quarks and leptons, as well as most composite particles like protons and neutrons, are fermions. So now you know what's a fermion. Okay. Now let me refresh your memory. What are half integer spin fermions? Half integer spin fermions are constrained by the Pauli exclusion principle, whereas integer spin bosons are not. The electron is a fermion with electron spin of half. The quarks are also fermions with a spin of half. The photon is a boson with spin 1, which is a typical boson spin. So I have to take you back. You watched the previous video. We talked all about this. What is half integer spin? In general, particles with half integer spin are called fermions. By half spin, we mean values 1/2, 3/2, 5/2, etc. Although it's not known if there exist particles with other spin numbers than half. We'll go to that video to tell you what is a half integer spin, and I've refreshed your memory. Now we're going to continue from where we left on this series on us discovering more about quarks. Now, a half integer spin is the result of half of an odd integer. A half integral adjective, all the particles we like to think of as real particles, like protons, neutrons, and electrons, have spin which is a half integral. That's 1/2, 3/2, 5/2, and so on, right? And I told you about half spin means that if from the position it starts, if it rotates, like, okay, let me see whether I can illustrate it this way. Of course, this is my thinking. Here we have x-axis, actually in 3 dimensions. We have z, we have like this and this way. I'm not good at drawing. This is z, this is y in 3 dimensions. But if say this thing starts at this point and say it's spinning clockwise, it's going clockwise, yeah, it's making a complete rotation like this. Now in half integer spin, you see this has come back to this, but half integer spin, it will come up to this point in a complete rotation. So it has to rotate twice to come to its original position. So what does half integral? Now we have another new terminology called integral. What does that mean? A particle with a whole number integer spin comes back to the same state after rotating around once. It will come back to the same state, like the one I've just drawn here. If it has integral 1, it will start here and it will go positive clockwise, and it will go like this, go back and come back to this position, complete 1. Okay, in 1 rotation it will come to 1. Now a particle with a half integer spin comes back to minus its starting state after whole rotation. So minus of where it started. For example, it started here. Now let's say this one, I think is more confusing. Let's draw a two dimension. So let's say it started here, then it will end up here. This is positive, of course, and this is minus. You can give any value here, 1, 2, 3, 1, 2, 3. Similarly, 1, 2 in the negative scales, and in the positive scale, 1, 1, 2, negative. You know, the coordinate system. This is positive if it goes this way. Up to this point is positive. It goes below here, it is in the negative state. It will go here, it remains in the negative state, until it comes back here. So you can see actually the negativity covers a lot. Below 0, this is below 0. Anything below 0 should be negative. Anything beyond 1 should be negative. But up here is positive and this is positive. So what is saying that this thing, when it starts here, if it's a half integer spin, it will come up this position, but it has to make a complete rotation. So this where it's a bit confusing. Now if it started here, it makes a complete rotation. It should stop here, but it stops here. So it means that it goes an extra half more in a complete rotation. What does that actually mean? It means that it goes fast. It goes fast, the speed at which it goes, because why should it start here, make a complete rotation, but stops here? This has to do with the speed at which it's going. And when you talk of a whole integer spin, it will come here and stop here, which is a complete one. So half integer spin particle goes faster, in my own opinion. I don't know what it means, because why should it go beyond how it go opposite where it started, right? Because it has made a complete rotation, 360 degrees, but it's not stopping at that positive point where it started. It stops at the negative part of it. It means it goes beyond that point, as far as I understand it, and that has to do with the speed at which it's going. So that's what I think. So a particle that have integer spin comes back to minus its starting state after a whole rotation. It has to rotate twice to get back to the starting point. So if it's 360 times 2, it means it has to rotate 720 degrees to come back to where it started. Yeah, that's what we call half integral. That's what it means, half integral. So what are fermions? I've told you what the fermions are. Now, according to what I'm telling you, the fermions are half integer particles. So they are this type of thing that stops at the opposite of point where they started. They started in the positive position, they'll stop at the negative position after complete rotation, and they have to rotate again to come back to the position where they started. So the example of this is a fermions, which does this. And what do you know what's a fermion? I've told you what's a fermion, right? So they have integer particles, and they're described by Fermi-Dirac statistics. They obey the Pauli exclusion principle. So two identical fermions do not occupy the same quantum state simultaneously. Okay, basically fermions can be classified into two groups. We have elementary and we have composite fermions. So elementary fermions are leptons, and we have in parentheses electrons, which means include electrons, neutrons, muons. Okay, then we have electron, then we have electron neutrino, then we have muon, neutrino, we have muon, then we have muon, neutrino. So in pairs we have electron, then we have electron, neutrino, comma, we have muon, then we have muon, neutrino, we have tau, and then we have tau, neutrino. These are all the units that are given and the states of these energy points, which we have named them variously according to these names, and they mean something in terms of mass. Like I was telling you, 10 raised to the power minus 15 m means mass. Actually it meant meters, not momentum. In the other previous video I confused, I didn't know what m is, what's really why it was there. So it means meters, 10 raised to the power minus 15 meters. If you go back to that video. Okay, so and that's not all. So we said our leptons, which have given you this electron, neutrino, muon, neutrino, tau, neutrino. Okay, under that, and then we have quarks, and in the quarks category we have up, down, top, bottom, strange, and charm. Okay, so we call quark hadrons, and we have also hadrons, that is quarks, and then we have hadrons. In hadron category we have neutrons and protons. You see, actually when quarks come together, they come together to form these things like neutron, proton, which are more stable. The others that are unstable, they are not included here. And this from these neutron, protons and electrons, that's where atoms come from. So you can see atoms have originated from these hadrons, and hadrons, quarks makes up hadrons. If you go to the previous video, I don't have to tell you all these things. Maybe you are following and you know what that is. So in hadron category we have neutrons and protons, okay, containing an odd number of quarks, containing an odd number of quarks, and a nuclei made of an odd number of nucleons. Okay, I have told you what nucleons are. As neutron and protons together make nucleons. Like example, we have carbonucleic 13 carbon, which contains 6 protons and 7 neutrons. So are considered to be composite fermions. I told you what composite fermions are. In addition, atoms such as helium-3 contain 2 protons, 1 neutron, and 2 electrons. Okay, helium-3 are also composite fermions. So helium-3 is also considered to be a composite 3. And I don't like going back and back, but I told you what are these composites right now. I'm not going to repeat it because it's like repeating the video. So that's it. In addition, atoms such as helium-3 contain 2 protons, 1 neutron, and 2 electrons. So we have 2 protons, 1 neutron, and 2 electrons, which are also composite fermions. Elementary fermions are the fundamental building block of both matter and antimatter. So elementary is very important. It's the fundamental building block of matter and antimatter from the elementary. And in the elementary category, I don't think I go back to say what are these, what are fermions and so stuff, because I've told you that already. Yeah, elementary fermions are leptons. No, this is not the thing. Yeah, guys. So you see, we are making a journey to know what are these things called quarks, which are the fundamental building blocks in nature. You can see that the quarks are also not just, even there are things we call quarks, which are smaller than quarks. I think, I don't know whether I have that on here. Yeah, maybe, I think prions or something, I'm not very sure. So you see, in our journey to discover the particles, we have come down to the fundamental particle, which is a quark, and the quarks form two up quarks, one down quark, one up quark, two down quark. Two up quarks, one down quark makes a proton. One up quark, two down quark make a neutron. Neutron and protons plus the electrons that is almost considered negligible in terms of mass make up an atom, and an atom will make up a molecule. You see, in that hierarchy we go down and up, and now below the quark, that's what we're gonna go next and find out what is actually below the quark, if there is any, because this is a fundamental. Fundamental means the elementary, the starting point for matter, and that's why we say matter. What is matter? Matter is equal to energy. Energy is equal to mc squared. Matter, and speed of c squared stands for what? Speed of light. And what's really, it's all about energy. You see, like when you say quark, it's a point of energy. It's a point of energy. And when you say 3 quarks, and they are going to make up a proton. So what is a proton? Isn't that also a point of energy? So with a different mass, and now we're gonna go to Higgs bosons and find out how it's responsible in giving mass to all the things in the universe, and it's called God particle. It creates mass. Otherwise things will be massless, and the universe will not exist without mass. I mean, there will be nothing with it like mass. I even wonder, when you say that particles exist in 3 states, matter. Now you see, you're talking about matter, and you say energy is equal to matter plus c squared is equal to mc squared. Energy is equal to mc squared, okay? And in 3 states of matter exist. Matter, is that what it is? Isn't that what it is? Matter exists in 3 states. What exists in 3 states? We have solid, liquid, and gas. And there's something that has weight and can occupy space. Now look, how does it become ice? What are the conditions? What's that has to do with thermal, the temperature. And temperature means what? Heat. Like now I'm feeling hot because the fan is not running, and it is heat and I'm sweating. So what is that? So it means the degree, the temperature, the way we name it is that condition which has a magnitude. It's not a factor quantity, I think. It's a magnitude quantity, like when you talk about temperature. So energy, right? Like when you talk about these quarks and other things, and we go down, right down, in my belief, it's nothing, I'm not going to quote anything, this is my own thinking, is that there is a point beyond which something does not go. Instead, it mutates to another state. Like when you boil water, when it's cold, you boil it, it reaches a point where, when the boiling point, it turns to vapor. Yeah, but it does continue to boil, and when it turns to vapor, it starts to disappear from the vessels where you are boiling it. Maybe I can boil one here, but you have boiled water, and you have seen this. So, and if you freeze water, it becomes ice, right? It becomes ice. You have frozen water in your refrigerators, and you have seen ice cubes. And if you expose it somewhere, you see something like the vapor is coming out of it. Now, how do you call that? Because there's no thermal. Is there thermal is working there at that scale? You will not feel it, but the ice is feeling it. It's changing from that condition to another. So, in other words, what I think is that there's a state below which something does not go. Instead, it changes to another state. Like if you rub your 2 hands and do this continuously, just do it right now as I'm doing it continuously, you will feel the heat is coming. What is the origin of that heat? There's a frictional force, right? When you wrap one hand against the other, frictional force and continues with that, you feel hot. Hot is coming. That heat is thermal. And my art of doing this is the energies, not energy of my body. So energies are doing things, are doing force energy, is something that makes something to happen. So how is that something that makes something to happen equals to matter times c squared? Yeah, matter, you are matter, you're made of matter. How is that? So because you're made of the quarks, okay? You can see the connection coming in. So this is matter interrupting each other like these, and this frictional force there, and the heat is thermal energies there. Thermal, we call thermodynamics, is being created. So we have to investigate and find out exactly how is this energy related to everything, and what is it, because we have just given it a name energy, but it's a physical phenomenon. What is this phenomenon? Like when you talk of electromagnetic, what are the four forces? Like we have gravitational, electromagnetism, we have strong force, we have weak force. See, we are describing what we observe around us. So please, as we continue this journey, we're gonna go to Higgs boson. I think that's what we should go to, and from there I think we'll move down now to the fields, and that will be our final point, because beyond the field nothing exists as far as our current understanding and knowledge is concerned. But for today, I think we shall end it there. Thanks guys for watching. Like, share and subscribe my videos. I'm sorry I'm not able to give you a lot of practicals because of the conditions surrounding me here where I am, but in future I'll be able to demonstrate to you lots of what I'm telling you. So please stay tuned, like my videos, subscribe to the channel and comment. So bye from me now, and see you in another one, in the next one. Bye.